Hi, my name is Andrea Detlefsen, and today I'm going to be giving a review of the events leading up to, including, and following Paul W.K. Rothman's folding DNA to create nanoscale shapes and patterns. On December 29th of 1959, at the annual meeting of the American Physical Society at Caltech, Dr. Richard Feynman famously challenged his colleagues to find a way to write the entire 24 volumes of the Britannica Encyclopedia on the head of a pin. He dared scientists around the globe to push the boundaries of current electron microscopy, calling for better resolution and more powerful technology, and even proposed several ideas for both writing and reading text tiny enough to fit on the head of a pin. Feynman's challenge marked the unofficial beginning of the race to miniaturize computers and information, manipulate single atoms to create patterns and shapes, and ultimately to create nanostructures that deliver drugs, act as robots, and perform features that were unimaginable during that time. Ultimately, this boom in miniaturization led up to Paul Rothman's development of nanostructures from DNA termed scaffold DNA origami. However, there was much work prior to his discovery. Some 20 years after the annual meeting at the American Physical Society, the scanning tunneling microscope was invented, leading to the ability to image and alter surfaces with resolution and precision that was previously unheard of. 10 years after the invention of STM, the ability to deliberately move and place individual xenon atoms on a nickel crystal surface was reported. As you can see in the sequential images in the figure to the left, this technique required the serial movement of individual atoms one at a time. As a result, this was a slow process. Additionally, it required harsh conditions as it could only be performed at 4 degrees Kelvin and under a vacuum. Following this seminal top-down technique, top-down meaning the method requires individual serial movements, many other techniques and applications started to pop up. To the left is one example, where researchers designed a dip pen tip using atomic force microscopy. In this technique, the AFM tip is dragged across the substrate with a deposit of an ink-like substance, in this case gold nanoparticles. Then, it is dragged across a different hydrophobic surface, where the gold particles will jump from the tip to the new surface, leaving behind a trail in the desired design. In another technique, researchers applied a layer of soft-landed nanoparticles, meaning that they were only loosely attached to the surface. Then, they dragged an STM tip across, removing a line of particles, like an etching, and leaving behind a particle-free design. Other techniques experimented with self-assembly using colloid chemistry, and some even used the movement of individual particles to study luminescent properties of silver nanoparticle clusters. In addition to these previously mentioned top-down approaches, there were also DNA-based and self-assembly techniques that predated Rothman's own work. For example, the figure to the left shows one group's methods for the formation of a DNA cube structure. As you can see, it requires several rounds of purification after the addition of each component, which is something that Rutherford strove to improve in his own work. Shown in the upper right is a figure from a paper that describes the use of computer programs to design extended DNA structures based on the geometry and folding characteristic of this biomolecule. Finally, the figure in the bottom right shows the schematic for a DNA octahedron. The assembly of this structure was documented shortly before Rothman's work and uses some of the same techniques, such as sticky edges, to fold the structure into the desired shape that he used. Rothman describes that his work was partly inspired by the current problems in the field of creating nanopatterns and structures. With respect to the top-down approach, many techniques required harsh conditions that were difficult to simulate and made procedures very hard to execute. Additionally, they required serial movement of atoms, making it a very slow process with little hope of parallel synthesis. In the case of current self-assembly methods, their tendency for extreme dependence on stoichiometry and purification processes made them cumbersome, in addition to giving low yield and poor quality products. It was at this point that Rutherman began his own work to overcome these obstacles. He began by choosing to work with DNA, as several others had done before him. DNA is unique in that it offers a set of highly specific interactions in the form of Watson and Crick base pairs, where adenine pairs with thymine and guanine pairs with cytosine, as shown to the right. Additionally, the combinatorially large possibility of DNA sequences was a very desirable quality, as it allowed for enough unique interactions that were needed for his technique. DNA self-assembly and small size were other key qualities, lending it to be a molecule that allowed for rapid, relatively hands-free synthesis. With these qualities in mind, Rutherman strove to create a new nanostructure synthesis procedure that eliminated the dependence on stoichiometry on purification, could be performed in mild and replicable conditions, and that had a satisfactorily large yield. He famously gave his method the charming name of scaffold DNA origami. In his paper, he describes a 5-step process that relies on both computer programs and handmade models. His signature technique involves the use of a long scaffold strand that provides the structure of the shape, as is implied by its name, and also the use of a host of shorter oligonucleotides that he called staple strands. The role of the staple strands was to fasten the structure in place by binding selectively to the scaffold strand. The figure below serves to illustrate that either linear or circular DNA could be used as a scaffold strand, as long as it was single-stranded. It is important that the scaffold strand be single-stranded, as it must be available to bind with the staple strands. The first step of the process is to create the desired geometric shape, like the square I have shown here. Then, fill the shape with double-stranded DNA, like those represented by the gray cylinders. The cylinders are trimmed to fit the shape exactly, but are always an integer number of DNA turns in length. Shown below is a representation of the double helix, where one segment equals one turn, which is approximately 10.67 bases, or 3.6 nanometers long. The number of turns indicates the width of the shape. Additionally, the helix height is approximately 2 nanometers. However, the height of the total shape is also determined by other factors, such as the crossover spacing and the electrostatic repulsions between strands. Finally, blue crossover points, where the staples will switch from one scaffold strand to an adjacent strand, are added, shown as blue X's. In step 2, a scaffold strand overlays the double-stranded helix in the raster filling pattern, as shown in the figure to the left. As mentioned before, the scaffold strand can be either circular or linear. Here I have shown a linear scaffold strand. In addition to the periodic crossovers that were placed on the shape in the previous step, the scaffold strand also creates scaffold crossovers, where it transitions vertically from one row to the next. It should also be noted that a seam could be created in this step, as will be shown later. In step 3, the computer program inserts staples in place of crossovers. These staples represent complementary DNA sequences that will bind with specificity to the predetermined points on the scaffold DNA, giving it stable structure. It should be noted that the staple strands are always antiparallel, which is required for a stable DNA structure. The bottom right figure shows antiparallel strands where the 5' and 3' ends of the annealed strands are on opposite ends. Additionally, the staple strands are inserted with a glide symmetry, meaning their minor grooves, which are illustrated in the bottom left figure, face alternating directions. This relieves strain in the twisting helix. Finally, it is important to note that there are no unpaired bases in the crossover regions of the staple strands between scaffold strands. Instead, the staple strands bend gently, leaving only a single phosphate backbone in the gap. In the fourth step, the computer program makes several adjustments to alleviate additional strain. First, it minimizes scaffold strain by shifting the scaffold strand slightly so that the crossovers fall tangent to the twist in the double helix. Because this shifts the position of all of the bases slightly, adjustments to the staple strands are also made accordingly. In the final step, nicks in the backbone are eliminated by merging adjacent staples. Nicks are points in the backbone where the edges of two staples meet and are marked by a small divot in the backbone. This merging of staples has the additional benefit of increasing the binding domain, or the number of base pairs made, which strengthens the overall structure and as a result increases the melting point. Additionally, it is common for staples to be merged across any seams in the structure to bridge the gap, as shown in the bottom figure. There are multiple ways to create bridges and merges, and although choosing a different system won't change the overall shape of a structure, it will change the weaving pattern, which can be observed in the atomic force microscopy images. Rutherman reports using circular single-stranded DNA from the M13-MP18 bacteriophage. He chose this DNA because it was naturally single-stranded, eliminating the need for separation of a double strand, and long, allowing for complex shapes to be made. It did, however, have a single hairpin region that was avoided to prevent any interference with base pair interactions. If a single-stranded scaffold was desired, the M13-MP18 DNA could simply be cut with a BSR-BI enzyme, as is shown below. This cleavage occurred in the hairpin region. In order to form the shapes, Rutherman mixed scaffold strands, stapled strands in about 100-fold excess, and remainder strands, which annealed with any tail ends in the shapes that did not require the full length. He allowed them to anneal at temperatures ranging from 20 to 90 degrees Celsius, and then imaged them using AFM. It was noted that he deposited all of the contents of the reaction onto mica without purification, but that only the formed shapes stuck for imaging. Here we have the initial results. From left to right, the shapes are a square, a rectangle with a seam, a 5-point star, a disc with 3 holes, a triangle with rectangular domains, and a sharp triangle made with trapezoidal domains. The bottom 2 rows show an example of a well-formed shape and examples of characteristic defects for each species, respectively. In the case of the square, the most common defect was an hourglass shape. Rutherman noticed that this distortion worsened with sequential images and therefore concluded that this defect was induced by interference from the AFM during imaging. The rectangles, shown in the next column, tended to form a long chain. Rutherman fixed this by altering the staples at the edges of the shape so that they would not stick with other rectangles. The stars formed with many fragments, which Rutherman proposed and later confirmed by using an untreated scaffold strand, was due to damage during enzymatic digestion from a circular to linear scaffold strand. The 3-hole disc also tended to form chains, like the rectangles. The rectangular domain triangles were held together by only one covalent bond at each vertice, and as a result experienced the same chain formation like the original rectangles. Finally, the sharp triangles formed with excellent yield due to the strong interactions between the surfaces at each face. Rutherman established criteria for yield as the number of well-formed shapes out of the total number of observed shapes in the series of AFM images. A well-formed shape consisted of no holes or indentations wider than 15 nanometers. It's apparent that the seamed rectangles, 3-hole discs, and sharp triangles had the best yields at 90% of 40, 70% of 90, and 88% of 78 respectively, and that the rectangular domain triangles were the worst by far, at less than 1% of 199 observed structures. Rutherman performed several additional experiments not shown, in which he changed the staple to scaffold strand ratio dramatically to test whether this would affect the yield of well-formed shapes. He concluded that only when the ratio was reduced from 100-fold to excess to extremely low values such as 2 to 1 or 1.5 to 1 ratios did the shape exhibit severe malformation across the board. In addition to creating nanostructures, Rutherman also used his approach to create surface patterns. When creating the design, he assigned all staples to either a 1 or a 0 pixel, 0 representing the pixels that would not stand out, and 1 representing the pixels that would. He considered using fluorophores or hairpins to differentiate the 1 pixels, but ultimately decided to use hairpins to achieve a difference of shading in the AFM image due to a difference in height from the nanostructure surface. Chosen staples would have an extra hairpin loop that would sit above the surface. These loops could either be situated in a rectilinear manner, meaning that they stuck on alternating sides of the surface, or in a staggered manner, meaning that they all appeared on the same side of the surface. The staggered arrangement ultimately yielded the best quality images. In addition to patterns, he also created extended shapes. These extensions could be either periodic, meaning that they would extend infinitely, or finite. To attach shapes together, he designed tetraloop hairpins with 4 thiamines that line the edge of the shape. They could interact favorably with the edges of other shapes, acting as sticky edges. He also experimented with covalent bonding, like was previously mentioned with respect to the rectangular domain triangles. Here we have the result for his extended shape and patterns experiment. Rutherman reported that these variations. Overall, his method was a success. He practically eliminated the dependence on stoichiometry, as shapes did not show widespread effects unless the stoichiometry was changed dramatically, as previously mentioned. He also succeeded in eliminating the purification steps, as his shapes were formed in a single reaction vessel all at once. He used mild conditions, demonstrating that these reactions could be performed in a range of reproducible temperatures at ambient conditions. He also succeeded in parallel synthesis in high yield, as many high-quality shapes and patterns could be synthesized simultaneously within a relatively short period of time. Finally, his method can be performed at a relatively low cost. There are several factors that contributed to its success. The first is strand invasion, which is the concept that even if an incorrect staple is already bound to the scaffold strand, it will be replaced by the correct staple when it comes along. This may be understood in the same way as an energy diagram as is shown on the left, where the most stable conformation, fold, or base pair interaction will prevail. Cooperative effects also contribute to the structure, where the binding of one correct staple stabilizes the scaffold strand and makes it even more favorable for the next staple that comes along to bind, a phenomena that is perhaps related to a better orientation in space. Finally, staple strands do not bind to each other, as they are designed to have highly specific interactions with the scaffold strand. There are still areas of improvement, though, and Rutherman states that there may be some limitations with created large and extended structures. Since Rutherman's publication, there has been much research done to advance his techniques and apply them to novel fields. Here are some particularly interesting applications, including variations on his original methods, nanorobots and biosensors, enzyme kinetic studies, and cancer/drug therapy delivery systems. I'll describe a handful of them in the upcoming slides. One group has made nanostructures using Rutherman's procedure, but with modified or unnatural base pairs, termed UBPs. 2 examples are shown to the right, where thymine and cytosine have been modified respectively. Their creation was a 6-armed junction, shown in the upper left figure. Below this is one of their results, illustrating their findings that modified base pairs sometimes strengthen the structure and result in a higher melting point. Junction 0, shown in black, has no UBPs. Junction 1, shown in red, has 2 UBPs, and the lowest melting point, meaning that a greater fraction of the structures are denatured at a lower temperature. Junction 2, shown in blue, though, has 4 UBPs and has a dramatically lower melting point in the left-hand region of the plot, where almost none of the structures were shown to have denatured around 50 degrees Celsius. This group proposed that these modified structures might be valuable in biomedical applications where durable structures are especially necessary. Other researchers have created a triangular DNA mesh, shown in the upper figure, that folds with the sticky edge method and is held together by angular staples. They folded this mesh into a variety of unique hollow 3D shapes shown below, from a sphere to a stick figure to a bottle and even the Stanford bunny. Another hot field is the use of nanoboxes as a drug delivery system. These hollow boxes can be configured with a variety of locking systems and have the potential to deliver drugs to a very specific site, perhaps a tumor, to improve target drug therapy and reduce side effects that often come with a lack of specificity of where drugs are active in the body. The bottom figure shows a lock that opens and closes upon being irradiated with different energies of light. A conformational change occurs when it is struck with UV light, causing the box to open, and an additional one when it is struck by visible light, causing the box to close. Enzyme kinetic studies have also greatly benefited from nanostructures. The top figure shows a nanovault that opens and closes upon interaction with an open and close key. When open, the reaction solution is exposed to the enclosed enzyme and the applicable reaction is able to occur. In this way, enzyme release can be engineered to occur with great precision, allowing for exact monitoring of enzyme kinetics. The bottom figure illustrates how the opening and closing of this box was monitored using FRET. One wavelength of light would be detected when the box was closed, and FRET could occur because the quencher and emitter were adjacent, and another would be detected when the box was open and FRET was not occurring due to the large distance between the quencher and the emitter. Another enzyme study creatively immobilizes single and double-stranded DNA onto a 2D DNA nanostructure to study two types of helicases. A helicase is an enzyme that unwinds double-stranded DNA, playing an important role in DNA replication. Like Ruthermond, they took advantage of atomic force microscopy's ability to detect different heights, as single-stranded and double-stranded DNA are different heights due to their different degrees of unwinding. They imaged surfaces both with single and double-stranded DNA and compared these images to an experimental sheet that had originally been layered with only double-stranded DNA after incubation with each of the helicases for 3 hours. In this way, they were able to use the variation in height over time to determine the certain kinetic properties of each helicase. Perhaps some of the most futuristic and creative applications are the creation of DNA nanorobots and sensors. The top figure shows a cargo sorting robot that can pick up, move, and deposit cargo in new locations based on guiding molecular interactions. It can even perform parallel processes. Another group created a DNA genosensor that was immobilized on the end of an optical fiber and exhibited luminescence selectively when a target molecule was bound. This target molecule could potentially be engineered to be any small molecule in solution that is desired to be detected. There are so many other cool applications of Rutherford's research. I have a couple listed here and mention them in more detail in my review. Some of them are catalytic RNA, which mimic the self-cleaving ribozyme of tetrahymena and could possibly be integrated into their natural DNA, DNA ink nanostructure stamps, and even studies that elucidate multiple enzyme pathways. That's all I have for you today. Hope you've enjoyed my review of the events leading up to, including, and following Paul Ruthman's folding DNA to create nanoscale shapes and patterns.